Let's move on to the next section, which is arc length. We have done integrals which calculate area. That's our very starting off Riemann sums to find the area beneath a curve. We have done integrals to find volume. We have our disk method for integrating volume, and we have our shell method for integrating volume, both of which are just two different takes on building up a Riemann sum where each individual piece is just a little snippet of volume. And in the limit, our integral is stitching all of those back up together. Well, what other dimensions do we have left to work with? Can we find, oh, I don't know, hyperdimension in 4D? Well, we can, but not for today. Let's actually step down a dimension and talk about length. So the technical term here is the arc length of a function. So we have some curve. For right now, our curves are in the XY plane. And most commonly, I'm used to these being y equals a function of x. But for right now, the picture I have is just some curve, not necessarily attached to a particular formula. So intuitively, I should be able to straighten out this curve and just see how long of a line segment that is. Now notice that here in the box, we have a curve in blue, and if I straighten it out, it is actually going to be longer than that box is wide. We had to fold it in on itself to fit it inside the box. So abstractly, we could straighten this out, measure it with a ruler perhaps, but I want something numerical. I want something where I can actually know what it is that I'm calculating, because I don't get to go in with rulers on my graphs of functions. So if I can relate this idea of the length of a curve back to Riemann sums, I will be in business. So let's see, in dimension 2, I say that rectangles are very nice pieces of area, and I will use rectangles to approximate the true amount of area for some figure, for some region. And in the limit, as I take smaller rectangles, my approximation will tend towards the actual value of the area. In dimension 3, like we've been doing this week, why we chop up the figure into pieces of volume that are easy to approximate. We've mostly been doing various kinds of cylinders with holes in them. Could have easily done cubes, perhaps. And as we take smaller pieces, the approximation gets more accurate, and we get the actual volume. So continuing this pattern, I want to take some pieces of length that are very easy to calculate. What's the easiest length I can calculate?